All right, everyone. Let's get started. So welcome to the Topos Institute and Strathclyde, I guess, I don't know, Intercats seminar. And today we're pleased to welcome Mario Román talking about monoidal streams. So take it away, Mario.
Thank you. Thank you very much. So thank you to David, to Toby, and Jules for organizing and for inviting me. I'm very happy to talk about this work here. First, because the Intercat has a lot of overlap with the research I usually do. Let me do this. And then also because I think this can be a talk that benefits a lot for an audience that knows lenses. So sometimes when I present this work, I don't make much emphasis on the connections with lenses. But today, I think I'm going to be detailing how monoidal streams are inspired by the structures defined in lenses. So most of the work I'm going to talk today about is joint work with Elena Labore and Giovanni De Felice. I'm going to give you the paper a bit later. So my motivation for today, starting with lenses, is that when we use lenses, so monoidal lenses in a monoidal category, the thing we're trying to model are single bidirectional interactions. We have this forward part and this backward part. And with that, we can model a bunch of things. And because these things are different and we can model them under the same structure, lenses are interesting. We model things like database update, we model Bayesian updates, we do things like open games where an agent gives some move and receives some reward and so on. And what I'm going to try to do today, explain in a very naive way, is I'm going to just try to repeat this interaction. We have a forward part and a backward part. I'm going to just try to do a forward and a backward part followed by a forward and a backward part, and so on. So the things we expect to try to capture with this structure now are, well, before we were doing programming with some change on the values, now we are going to try to do things like Dataflow programming. If we were doing things like open games, perhaps now we can try to do repeated games. Or if we were doing some stochastic functions with updates before, perhaps now we can do stochastic process. So I'm not going through the literature in these things because I think you already know it, and also because the previous talks on this seminar are detailed very well. So this is going to be my main motivation. The motivation from programming comes from a paradigm of programming that is called Dataflow programming. So in Dataflow programming, every declaration is going to be a sequence of values. So usually when you do imperative or functional programming, you do a declaration and that has a fixed value. When you do Dataflow programming, now every one of your declarations is going to define a sequence of values. Each one of these values on the sequence can depend on the previous values. So for instance, here I have code. This would be valid code, I think in Lucid, that defines the natural numbers. And it just says, well, the natural numbers are a stream of values, a sequence of values that starts with 0, and it's followed by 1 plus the sequence of the natural numbers. So we can do more complicated programs. We have things like this operator, this followed by operator, this wait operator, this late stream. And with that, we try to construct streams from smaller pieces. So what are the advantages of this paradigm? Well, we have an elegant syntax. I think we can say like something writing Fibonacci, something like this. It's quite elegant and represents what Fibonacci does. Then we can have signal flow graphs. And I found this particularly interesting because if you go to the manual on Lucid or Lustre, you will find that the manual is already using string diagrams. Like on the cover of the manual of the language, there is a huge string diagram. So it feels something that we should be able to do with monoidal categories already. And we have good semantics for these things, at least on the Cartesian case. And the Cartesian case, this has been very well studied, and is the thing I'm going to present to you first, and then we are going to try to extend them to the monoidal case. So what we are trying to provide here is the semantics for the monoidal case. Okay, and you have some example languages. I have listed Lucid and Lustre. There is this Lucid synchronous, which is closer to the thing we are going to do, and there are other. So what are causal string functions and what is the work that is already done? So basically, there is work on the Cartesian case, and it has been done by Gustavo and Bene, this paper called Comonadic Notions of Computation. and then by Sprunger and Katsumata when they do these delayed traces. And the idea is that you take the semantics for these things to be causal string functions. So a causal string function from one sequence of sets to another sequence of sets is just a family of functions. This could be also done in any Cartesian category, really. It's just a family of functions that goes from x0 to xn to yn. So this is saying, if we take the natural numbers to be indexed in discrete time, this is saying at the first moment in time, we have a function from x0 to y0. The second moment in time, we have a function x1 to y1, but it's also taking the previous inputs. And on the moment 2, we will have the new input, but all the previous one, and with that, we generate the following output. So these are causal because every y is not going to depend on the future of the x's, so every output already depends on the previous inputs. For a category theorist, you can say this is the co-Kleisli category of the non-entity monoidal comonad. So we have a monoidal comonad that does precisely the thing you would expect. We construct the Kleisli category, is monoidal. That's the category of causal string functions. We have an extra structure in this category, a bit of extra structure. This extra structure is given by this trace-like operator. It says that if you delay some input, but you can produce it on the output, as we are doing here, you can always take the output you're producing and feeding it back to the input. You do this with a delay of 1 unit of time, but you can do so and you get something like a trace. And also because we are using coalgebras for all of these, you can apply coalgebraic reasoning and you can use co-inductive arguments. So the framework is really really solid, elegant, and interesting. The problem is when we try to go past the Cartesian case, because you want to perhaps to do some stochastic program or some quantum program or something like that, and then you don't want to require Cartesianness, and it feels like everything should work exactly the same. So perhaps we won't have this copy, or it's not going to be natural anymore. Let me put this with, so a copy like this isn't going to be natural anymore. Or you are going to have a syntax when you write your program that doesn't let you duplicate variables. But apart from that, it seems like it should be a pretty smooth pass from Cartesian to monoidal. However, if you try to go by just generalizing the comonad that we saw before, you can still define it in every monoidal category. You define as a monoidal tensor product like this. But the problem is that this functor, this non-entity list functor, is monoidal comonad. It's a monoidal comonad and gives you all this structure if and only if the category is Cartesian. So the problem here is by an argument that goes very similar to Fox's theorem, you can show that if this functor have the structure of a monoidal comonad, then you have your category supplying comonoids. You have comonoids that are natural uniform in every object. So then it's Cartesian. So the problem is that then we cannot extend this approach directly to Cartesian categories. So we need to try to find a different route. So let's go back to what are monoidal categories and how do we interpret processes in monoidal categories to try to get some motivation for the thing we're going to try to do today. So if you take the process interpretation of monoidal categories, we get that the objects with like some resources and the morphisms are some processes transforming these resources. So morphisms A to B could be processed with an input A and they produce an output B. This, of course, is not the interpretation that you use all the time of monoidal categories, but this is the one that you are thinking when you speak about processes. However, most processes don't work like that. So if you're thinking of drivers or servers or something similar, you're going to be wanting to take multiple inputs and producing multiple outputs. And that is not possible if you are using just morphisms on your monoidal category. So a bit of the claim that I want to make here is sometimes we want to use these open diagrams or perhaps repeated diagrams that they interact with the rest of the string diagram of the monoidal morphism in ways that are not just by input and output. And because I was working on these things, I tried to apply this solution to the problem. So I'm going to try to tell you what we find there. So let's go back to my presentation. I was saying that monoidal lenses or optics are modeling single and bidirectional interactions. So we are going to have something like this. And now if we want to model repeated interactions with an optic-like construction, it feels that we should do this infinite repeating diagram. That's something like that. So this feels like an idea that makes sense if you assume that this is the way we are going to do interactions. So let's just study this construction, and we are trying to see if this works for giving semantics to Dataflow programming. So I'm going to be formalizing this construction, how we do it, and how it gives semantics to Dataflow programming. The thing we are going to do is that every time we have a monoidal category sim, we will build another symmetric monoidal category of stream processes that has all the nice properties that we were expecting from our category of causal stream functions. It's Cartesian when the base category is. When we apply it to set, we are going to get causal streams again. When we apply it to stochastic functions, we get a notion of discrete control stochastic process that exists in the literature. And then if your category, you want it to be symmetric premonoidal, effectful, fried category, it still works. So it has a bunch of nice properties that we wanted to ask from such a construction. Okay, so all of this is on this paper, Monoidal Streams from Dataflow Programming, which we recently published. This is joint work with Elena Labore and Giovanni De Felice. And so the work had as initial motivation to try to study some repeated stochastic processes. But we found that this framework was apparently good, and then we started working on how it could be used to model Dataflow programming, stochastic processes, and things like that. So all the definitions I think I'm going to use, or most of them, are you can find them there, and all the proofs are there, I'm sure. So let me give you now a synopsis of what's on the paper and what's on this talk. So on the paper, we'll go through three definitions of monoidal stream. We give all of them in terms of a universal property, but then we give some explicit construction for these universal properties. So first we give the definition, and then we show you that there is a construction that realizes this universal property. And each one of these constructions is a quotienting of the previous. So the first one is going to be a very naive construction, but I think it's useful conceptually to have it. Then we're going to quotient the elements of this construction, and we're going to get a more refined construction that is a free category with feedback. So I'm going to explain what categories with feedback are. And finally, we're going to still quotient that and get this definitive notion of observational streams, which are the ones that we are going to take our definition of monoidal streams. And this can be shown to be the universal solution to a fixed point equation. That's the universal property that we have for them. So we have two known cases, which are the classical ones. So we will have the causal stream functions, and we have stochastic streams that follow as a particular case of this construction. So this is a good sanity check, because it's not just that we are getting the general framework or we are generalizing it, but also we get this notion of control stochastic process from our definition of monoidal stream. And then there are many other avenues for extending that. I don't think I'm going to enter on the details of those. Okay, so I'm going to go pretty quickly about what's the quadra that we're going to use, because I'm sure you probably know most of it. But the idea is that when we want to solve functor fixed points, so equations like this, what we want to find is the final quadra of this functor f. Why? Because by Lamprecht's theorem, we know that if a final quadra exists, then it's going to be the final fixed point. So coalgebras are things like this. Morphisms of coalgebras are natural squares, commuting squares like this. And when this morphism of the coalgebra is an isomorphism, we say it's a fixed point. And then by Lamprecht's theorem, we know that the final quadra is a fixed point. So that's a way of finding fixed points. Of course, we need to be able to construct these coalgebras, and for that we have Adame's theorem that says something that may make sense if you think of real analysis. If you are trying to find the fixed point of a function in classical analysis, one thing that you can do is just try to apply this function again and again to some value, and perhaps it converges. If you're lucky, it converges, and then you have found a fixed point. The same idea can be done with functors. You're going to compute this limit of applying f repeatedly to the terminal object of your category. And then Adame's theorem says if this limit exists and it is preserved by f, so it's a fixed point, then it's going to be the final fixed point. It's going to be the final coalgebra. So this is our way of constructing coalgebras. And with that, we can go to the definition of monoidal streams. So I'm going to start by the definition of streams, the classical ones. And I'm going to argue that I like it because it's really elegant. So we should try to do the same thing for monoidal streams. So the definition, the classical definition of stream says, a stream with types A0, A1, A2 is an element of A0, together with a stream with types A1, A2, A3. So this is not circular, this is conductive. And that means that we are going to be able to extract a mathematical object from that by computing the final coalgebra of an equation that is described by this sentence. So we have this slogan that gives us an equation, and we try to find the final fixed point of this equation. So how do we do that? Well, now is where we put all the machinery that I was describing before. This is just an example of how you do these things. We just have some operator, this thing, that is defining the right-hand side of the equation. It's going to take some family of sets indexed by n, some function that gives strings. So it takes some family of sets and gives you a set, and it's an endofunctor of this. So this is the definition of phi, is giving us the right-hand side. And now by atomic, if I want to try to find some solution to this fixed point equation, I'm going to just apply phi repeatedly to the terminal functor. You do that, the thing you get is this limit here that goes from 1, and then with the projections A0, A0, A1, A0, A1, A2. And when you compute that limit, this is the product of all the AN. And this is a solution. So the problem with this is at the end of the day, we need to check that this is still a fixed point. But if it is a fixed point, then we know it's canonical by Adam's theorem. So we check that it is a solution, and we can do so because this is just to reorganize the products. And we know that this is the thing we were defining. These are streams over sets. Okay, so this is elegant. So I claim, let's get that it's a good idea to try to do the same thing for monoidal categories and try to get our construction. So before we do that, we need to consider not only streams, but also control streams, because monoidal categories is not that we are going to be done when we define the elements. We want to define the elements with some input and some output. So first we say a stream function now from x0, x1, x2 to y0, y1, and y2. It's going to be a function that goes from x0 to y0, and it communicates through a memory channel with some stream function that does the rest of x and goes to the rest of y. So the thing I'm saying here is now when you get some x0, you're not only going to write something to the output, you can also write something to a memory m, an object that you can choose when you define the stream. And if you write something to that memory m, then you can use it later on the rest of the stream. So here you have exactly the same thing. You have again a functor that defines a fixed point equation, and we can try to now compute it. I need to justify two things. First, why are you putting a memory channel? What happens if you don't do this thing of the memory channel? If you don't do the thing of the memory channel, then you would just get a sequence of functions going from x0 to y0, then from x1 to y1, and so on. So this is a way of relating the first function to the rest. Like if this is a process, it should have some memory. It could remember what happened before and use it on the rest of the process. And then I think the second one is how do we go monoidal? And now is the moment where we change the Cartesian product by a tensor. So if we did this at the beginning, when we were talking about this previous comonad, that would not work. If we do this now this can be interpreted and we can give some sense to this in monoidal categories. The idea is if we interpret monoidal categories as theories of resources, when I have something like this, I'm saying you're going to be given some inputs, this x0, and you need to decide what to do with them. You can either send them to the output, this is y0, or you can either save them for yourself in the future, and this is that m. So this is now the fixed point equation that we are going to try to solve. You want to find what is the functor here that solves this equation, this t. So how do we do that? It's exactly the same that we did before with streams. So we define this phi. This phi can be applied repeatedly to the terminal profunctor, which is just 1. You obtain a limit like this. And I'm not going to go into the details of the computation, but then you use that some coproduct commute with some limits. Then you check that it is already a solution because product distributed were the co-products. So because of abstract considerations, you can check that this works. And we get a definition of monoidal stream, which is this one here. So first definition of the paper and first theorem is an intentional monoidal stream is a family of objects, the memories, and a family of morphisms. And each one of these morphisms is going to take some memory from the past, they input and produce a new memory and an output. So here we are saying that we are choosing the memories and then just giving all the morphisms indexed by time that give this monoidal stream. And then we show that the set of monoidal streams, depending on input and outputs, is the terminal fixed point of this equation. This is what I just was showing to you a moment ago. Nice. So this is the first definition of monoidal stream. So now I'm going to explain why this definition is still problematic. First, let's try to interpret it. So how do we interpret a monoidal stream? I was advancing before that we were going to have these open repeated diagrams. And this is the thing we defined when we computed these fixed points. Because we have a family of functions, a family of morphisms like this. And if you try to draw them, you get something like the thing you have here. So you are going to have x0 going to m0 and y0. Then the first step is going to take the previous memory, a new input, and produce a new memory and a new output, and so on. And you can interpret these things as they are being connected. So the memory of the first step goes to the second step, the memory of the second step goes to the third step, and so on. If you put all of them together, you get something like this, get the following open diagram. So we are really doing these open and repeated diagrams that I was speaking about before. Now, there is a problem with this approach. I have been using coproducts to choose the memories, and this is a bit too explicit. What I mean by that is that having a memory such as A times BC is different from having a memory AB times C, which makes them not to even be a category. So these monoidal streams, as we have defined them before, are too explicit. What's the problem here? Why do we want to be a bit more subtle when defining the memories? If you go to the drawing here on the left, I can define the following two intentional streams. So the first one takes an F0 and an R as the first step, then F1 and R1 as the second step, and so on. The second stream is just using F0 as the first step, then R0 and F1 as the second step, then R1 and F2. These two things are different in some sense because we have defined them to be different monoidal streams. They would even have like different memories here. So these types don't even need to be the same. So we know that they are different. However, morally, they should be the same because the only thing we are doing is sliding down and up. These are 0, R1, and so on. These two things should be equal. So we are going to ask precisely that. We ask now that the definition of an extensional monoidal stream, so our second definition, is an equivalence class of intentional streams under the minimal equivalence relation that contains this relation, this equality here. So this feels a natural thing to ask to me because I would have been thinking of these things as coends instead of coproducts. But I claim that even if you don't like coens, I can justify this definition to you. The interesting thing is here, if you quotient by this equivalence relation, you get coens. And even if you don't like coens, and this feels, so we had a complicated formula, and now we are quotienting by something also complicated, I can try to justify that this still makes sense. And the way I'm trying to justify this, these extensional streams, is by saying that they have still a universal property. The universal property can be done in terms of the feedback diagrams that we were seeing at the beginning. So imagine you forget about all of this and you want to define a new framework that does the same thing. It could be fair to assume that you want to give me some notion of feedback, and that notion of feedback needs to satisfy some properties. The properties that we are asking, we can all agree, I think, on these properties, just that the feedback is natural with respect to the morphisms is not touching. Then if you take feedback multiple times, that should be the same as taking feedback a single time. And finally, you want the feedback to allow sliding, right? If I have some edge here, I would like the feedback to allow me to slide to the edge on the other side. So here I can choose this to be any functor, any delay functor. It could even be the identity, and then you have some notion of weak trace, where not all the actions of trace are satisfied. But even in this weak axiomatization of feedback, if you give me some framework that has these actions of feedback, where you already have simulated extensional streams. Because the thing we prove is that the extensional streams are the morphisms of the free category with feedback over that delay functor. So there is a natural delay functor in C to the n, that is the one that takes a sequence of objects and just puts at the beginning the monoidal unit, and then just delays every object by 1 unit of time. And if you construct such a feedback functor on some category that contains C to the n, then you are going to contain also extensional streams. This has a nice interpretation in terms of diagrams, because the thing we are saying is that the feedback syntax that I was presenting to you at the beginning for the signal flow graphs can be interpreted in terms of extensional diagrams. And the interpretation is just like you are going to do this de-looping, right? You are going to take the diagram and you're going to be reading it from top to bottom every time. And that way you get your extensional stream. Okay, so now you can reason with this syntax. You can reason by sliding things through the feedback and so on. And there are some examples on the paper. I think I'm not going to enter on the details of how you do that. But I'm going to still not be satisfied by this construction, because there are some problems that are a bit more subtle now. But it happens that if you construct this over a Cartesian category, the thing you get back is not a Cartesian category anymore. And the problem is that there can be some morphisms that do nothing but just save things to memory and keep them in memory. So the problem is, even if I allow myself for sliding, even if I can slide things up and down, there is no way I'm going to prove that an identity that doesn't touch anything is just the same as discarding. So there could be processes that just keep something in memory without interacting with the world. And I cannot show that these are the same as just discarding. But observationally, I would want them to be the same. I'm not going to observe anything different if I have some process that doesn't interact with anything. So I want to still quotient by something, and this is observational equality. And with this, we get to the final notion of monoidal streams. Those are observational streams. I'm not going to go into the details of how we define observational equivalence, because I think those are technical and not that interesting. But the idea, the intuition is that we are going to consider streams up to some future. So I'm going to consider that two streams are equal if they are equal when I truncate at any point in time. So I just truncate the diagram at some point. And then I can consider, are they equal if I add something up to some future? And if they are, then I consider them to be equal. So now this is already a bit of an extra complication that we need to add to this framework. So it would be nice that we justify it. So the thing is that this is not only a reasonably standing rule, it's actually observational in some sense, because the thing this rule gives to monoidal streams is that it makes them be the final coalgebra of a functor. So we're going to get monoidal streams as a final coalgebra, and we can now compute them again. So this is the thing I was doing at the beginning. Then I started quotienting by a bunch of things. And now the claim is we can still recover them with all the quotientings as a final coalgebra. So now the claim is intentional streams. The first version that we saw at the beginning are the canonical fixed point of an equation like this, with a coproduct here. Observational streams with observational equality, as I have defined them at the end, are still the final fixed point of some equation. They are the fixed point of this equation, which is the same one that we are just substituting the coproduct by a coen. This doesn't work in all categories. This only works in some well-behaved categories. And now we're going to go into this. But I think the important thing here is that at the end of the day, we have taken this intuition that we have of what monoidal streams should be. We can go through all the process of getting the right notion of equality. And then at the end of the day, we can still recover them as a final fixed point of a functor. They are a final coalgebra. So, okay, but why doesn't work in all categories? We only ask on the paper that the categories have a condition that we call to be productive. But it's just a technical condition to say that there are no complicated things. So why this fails in a general monoidal category is written on the paper and detailed in the paper. I think it's not much interesting. The idea is that limits don't commute with coends as they do with co-limits. And the intuition, the practical idea you need to take away is that if you have some category where you can always factor a morphism as some morphism and something else, but this morphism is still like smaller, so you can still factor them into a chain of morphisms, then that won't work. Then you will have that this limit doesn't commute with this coen, and this won't be true. So I'm saying that this is something that doesn't happen in most cases. I think it's something pathological that won't happen in your categories of processes, because you can show that if your category is Semicartesian or Cartesian, then there is nothing to worry. If your category is compact flows, then it's nothing to worry. Markov categories, then they work perfectly. Freely generated monoidal categories work perfectly. So most of the theories of processes that you think about when you think about monoidal categories don't suffer from this problem. However, we cannot apply Adamic in general. So we cannot show with any trick of Adamic's theorem that this is a final quadrant. We only show it in a bunch of categories of interest. So what are those categories of interest? I was saying that a point of this framework would be to recover classical examples. So first of all, the thing we need to do is to recover the classical case of causal string functions. We were saying at the beginning that causal string functions were the natural solution when we have Cartesian categories. So we can prove now that monoidal streams in a Cartesian category are precisely causal string functions. You can do it by coen calculus, you can do it explicitly, and even compute with Adamic's theorem again that the final coalgebra is the one you expect. So causal string functions. The details are on the paper, but this is easy after the definition because you are using just properties of the coen. And we can also recover control stochastic processes. So a control stochastic process is a classical definition on the literature that says that it's just a family of stochastic functions. So going from x0 to xn to some outputs, so to some joint distribution of the outputs, so y0 to yn. And they satisfy some causality property, some property that says, well, the future things, so the input x n plus 1 should not affect the past. And this is formalized by saying that this diagram here commutes. So if you forget about one input and then compute, that should be the same as computing and then forgetting about the last output. This is a way of saying that causality is preserved. And you can show that monoidal streams over the category of stochastic functions or cluster of D coincide with this notion of control stochastic process. The proof is long, is more difficult than I was expecting, but I think it's really nice to have it because then it's not only a sanity check that we are recovering the classical framework, we are also getting some examples that make sense on what we want monoidal streams to be. So we have these two examples. On the paper with those, we play a bit and we do things like random walks here or Fibonacci sequences, or even this is the Ehrenfest model. So we can play with a bunch of natural examples of stochastic process and stream functions. Okay, so to recap, now that we are here, I have presented you a definition of monoidal streams. I have justified this feels like a natural definition. And then the thing we were seeing is that we can still recover all the classical results on this area. We can still recover the classical framework of causal string functions. We can recover some framework for stochastic functions. The problem is, how do we reason with these monoidal streams? Because from the definition I have given you until now, it feels that they can be complicated objects, or sometimes even if you can draw them, it's not clear when you're being formal if you use string diagrams, because we are using these weird repeated open string diagrams, right? And even if I am convinced, because I was putting some effort into try to formalize this, this can be confusing when you do it for the first time. Which are the moves that I'm allowed in these repeated diagrams? So here is where the coalgebraic description comes in handy. Here is where it shines, because now we can reason using co-induction about these monoidal streams. So we were saying that they are final coalgebra. They are final coalgebra because they are a final fixed point of this equation. So now we can give this co-inductive definition of monoidal stream and say a monoidal stream from x0, x1 to y0, y1 is going to be a triple of things. It's going to be a memory. This is the first memory of the first step. Then it's going to be a now step that goes from x0 to the memory and y0. So it needs to decide which thing saves into memory, which things go to y0. And then a later part, which is another stream that now it takes the memory and the previous inputs to the outputs. We need to quotient this by something. So we are going to quotient by this equality that says that we have some R that goes from one memory to another, translating from one memory to another. This is the same equality we were quotienting at the beginning. And it is such that the now part coincides after you apply R, and the later part is still equivalence when you apply R to the other side. So this is a way of saying that this trick of sliding R up and down still works here, and that we can define this equality coinductively. So if I want to show that two streams are equal, I show that they are equal at the beginning, and then by coinduction, I extend it to the rest of the stream. So this requires some changes to the way we reason. We will be reasoning with streams that have some extra structures, so to strengthen our conduction hypothesis. But I'm going to show you an example of how you do this, because I think it's very, very pleasant at the end of this technical thing. So you can forget everything about the definition of monoidal stream, take this last definition with coinductive things, and then imagine you want to show that monoidal streams form a category. So you want to define sequential composition of monoidal streams. So how can we do that? If we do that with diagrams, we will do the thing I have here on the right. So this is the definition we would do. We would have some pair of string diagrams, and then we know how to put them together in a way that they form a new monoidal stream. How do we do that with coinduction? So if I have some string f and some string g, I'm going to define the composition, and I just need to define first the memory they're going to have on the first step. This is normally easy. Then the thing they do on the first step, which is a string diagram like that. I can use string diagrams to define that because it's just a Morphism monoidal category. And then say, and I extend by coinduction the same definition to the later part. So the thing we're going to do is just to repeat this definition again and again here. Because this is a conductive definition, this is fine. And we are just repeating again and again the same construction that we are doing with string diagrams. The only problem is the first step that is going to be having here some monoidal unit. This is necessary because we want to regard the first step as the same thing as the rest of the steps. But if you don't do that carefully, it could seem that the first step is different from the rest. Like if I delete all this part, it could seem that the first step is different from the rest of the composition. However, if you see it like that, it's just the first step that is a monoidal unit, but it's always the same pattern, repeated again and again. So these are the kind of proofs we do in the paper. Then you need to prove that it is defined, well defined with respect to the equivalence we have imposed. So this is actually something that you can do easily with string diagrams again. I'm going to enter into the details, but the thing I want to sell to you here is that this feels very pleasant. Writing proofs on this framework was really nice because you can use two things. On one hand, you can use string diagrams, as you would usually do on a monoidal category. And then by coinduction, you extend that to infinitely repeating diagrams. So the proofs feel very easy and very nice because you can use both string diagrams and coinduction. The interplay between both makes for a really nice framework. The proofs are on the paper, well detailed. So this is just an example of how we would reason. And in this way, you can define symmetric monoidal category of strings. You can show that it has feedback. You can show all the properties that you would expect it to be. You can show that it has an identity and object functor from C to the N, then a functor that goes from C to that category, and so on. So there is out of a structure that you can recover by reasoning coinductively on monoidal strings. So I think this is most of it. So to recap, now that we are here, we have given this definition of monoidal strings. We have tried to justify it using coalgebra, but also using string diagrams. So the intuition from the beginning was that we wanted to do these repeated string diagrams. And then it's not only that we are going to recover the previous frameworks, we are going to give some new cases when you're interpreting in different monoidal categories. But also, and we were talking about Dataflow programming. On the paper, you will find this part where we try to interpret, again, the same Dataflow programming language that we were seeing at the beginning in terms of these monoidal streams. And these monoidal streams can be amenable to reasoning conductively with them. Okay, I think this is all. So now for the final part, I would like to go to some questions that I think can be interesting. And even if I think a bit before time, you can also take that for questions. So after selling all of that, the problem is what are the other examples that we have? So most of the examples I have tried to sell to you are monoidal, and that is fine. But when you talk about processes, most of the categories that you find, and this is very obvious when you try to do implementations, are not monoidal but pre-monoidal. So this will be a symmetric monoidal category again, but the interchange law symmetric monoidal categories won't work. So this is not going to be true. And the main example are the classic categories of strong monads. So if you take some strong monad overset and you compute the classic category, it is not true that the effects commute. So if you are describing programs, doing the following two programs is different because one of them is going to output in one order and the other one is going to output the phrase backward. So that's not what you want. And then you ask that interchange is not always true. This construction of monoidal streams, however, extends nicely to pre-monoidal categories, and this is something that you can do again reasoning by co-induction. So you take the same definition, you may want to change where the coen is taken, so you may want to change that is taking what's called the center of the pre-monoidal category, but apart from that, the construction is the same. This is important because it gives us another source of examples. I was trying to sell you functions, then stochastic functions, you can do partial functions, similar things, but many of the examples of processes arise as classic categories of monads or comonads, so you want to cover these as well, and these are pre-monoidal categories, not monoidal. So this is the details of the implementation, and the only thing is that you want to ask, and I think now the string diagrams make this really clear. You want to ask that this R0 is not going to always commute with the whole. It's just always, this is going to commute with the whole whenever it is a member of the center of the pre-monoidal category. That is when it's allowed to commute with any other morphism, to interchange. So, okay, so in summary, and I'm going to go back to the summary of the talk. Given any symmetric monoidal category, C, but I'm also saying you that pre-monoidal works the same, we can build a symmetric monoidal category of stream processes. And it has the nice properties that Dataflow programming was having with causal stream functions. So we have still an entity object functor from C to the M. We have a delay, and this delay is defined in the natural way in C to the N and then extended to the category of monoidal streams. We have some notion of delayed feedback in these monoidal streams. You can define co-inductively. You can have this quadratic description that makes reasoning easy. Then we still recover causal stream functions. In the Cartesian case, we have stochastic processes, and we can have a source of examples when we use other pre-monoidal categories. So I think with that, that's all. There are other things that I can enter, but I think that's more interesting. We go to the questions, and if any of the questions arises, I'm happy to answer. So I leave you with the rest of the work. We have used the framework of feedback, categories of feedback from Causal and Walters. Then Spruger and Katsumata do this discussion of the delay trace. Usalo and Bene do the same thing of algebraic streams, but they do it in the Cartesian case. And then there are many other papers that we're going to see are related to the thing we are doing. So the interesting thing, for instance, on this arrow loop, is that we can still use syntaxes that exist for these monoidal streams. This is a way also of checking a sanity check, the fact that you recover things that were in the literature in some form. So with this, I think I'm going to finish. I think I finished a little bit before time, but if the time can be for questions, I'm happy. Thank you very much.
Thanks, Mario. Okay, if anyone has a question, just raise your hand using the reaction button, and or feel free to just unmute and ask. Maybe if there are no questions, you could move to a.
I was thinking there is this question by Jules on the chat that I found really interesting, which is like Semicartesian strikes again. That condition shows up unreasonably often in the optic world. I think that is an interesting thing because when I was saying, for instance, you can have a lot of pathological examples where this framework doesn't work. Most of them can be made to work if you assume that you have a natural discard. And the reason why you want this natural discard map, this semi-Cartesian structure, is because when you have a coin, there is this trick that tries to get rid of all the naturality of the coin just by saying, well, discarding is natural. So I have a natural map from any object to one, and that is a natural on the object. So that way you can get rid of a lot of the complications when you do coin. So perhaps that answers the question, why is semi-Cartesian so important when you do optics? And it's because part of the coin and a monoidal category, you can get rid of the worst part by using semi-Cartesianity, if that makes sense. So sorry, David, if there are any other questions?
I guess I can ask a question. So I'm just trying to imagine how you turn this into practice. So I think the simplest case is if you have an optic that's representing, I think the simplest possible case is if you have an optic that's representing a how's it called? Christina's thing, an automaton with a readout and I'm blanking on what it's called.
Yeah. So there was this way of encoding. I think this to David, perhaps there is this way of encoding these automata with lenses, right? So when you have the SS on one side and AB.
So you have a map from states to outputs and a map from current state times input to next state.
Exactly.
So I think that the simplest possible instance of this would be talking about making one of these machines interact with an environment, and you get a stream of states. Yes.
So if you do that, and then you allow me to quotient that S and S paired by the naturality, then the thing you get is so there is this theorem by Cathy, Sabadell, and Walters that says that the thing you get at the end of the day is a morphism of the free category with feedback. So when we try to quotient when we try to do this construction of extensional streams, we secretly are using exactly that, so that you can construct with a lens, in some sense, you can construct a mini machine. And the naturality there is the condition that gives you this third axiom. So if you create a category where inputs are in A, outputs are in B, and then these two S's that a lens that have on the other side of the lens, and use that to describe a mini machine automaton, then that thing is a morphism, precisely a morphism of the free category with feedback over your monoidal category where you describe the lens. So it makes, I do agree with you, it makes a lot of sense because it's the same construction in some sense. Just here we are allowing it to vary on time, if that makes sense. Perhaps
you're allowing the set of states to vary in time, is that what you said?
Yeah.
I have, I guess, another question, but if anyone else has questions, we should let them go first.
I think they'll raise their hand if they do, yeah.
So is this inherently discrete time? So you can talk about dynamical systems in continuous time by sticking the right kind of bundle in the right place.
So I would like to, but I don't know how to do that properly. And somehow I would like to keep the same framework and extend that elegantly to continuous time. But I don't know how to do that yet. So the idea here is that from the beginning, I was setting this up that I would have this CN on the base, and then you cannot escape from that. So perhaps there is a way. I would totally believe that there is a way, and I would like to have a way that somehow preserves all this structure. Perhaps you cannot resolve any more quadratically, conductively, but there is something else that you can do, or perhaps you don't have the same feedback, but you still have something that makes sense. Feedback. I don't know how to do that, but I think there should be something to be said there. But the construction that I have done today is completely discrete time from the beginning to the end, and it also simplifies me.
It's a shame that Matteo is. It's a shame that Matteo is not here, because he has. I mean, he thought about this question a bunch last year, but he was really fixated on not assuming discrete time, which led him down a totally different route.
Yeah, because that's the point. Like most of the structure that we get, I would not know how to generalize that to continuous time. Not saying that it doesn't work. I think something should be doable, and I don't know how that would relate to the thing on dynamical systems that's given on my side. I don't know. So we tried for the simplest, most naive case. Also because the motivation is Dataflow programming, and there you are somehow always assuming discrete time, which is a simplification that makes everything easy, even if you don't have continuous time.
I mean, we're also in a situation where like 90% of our use cases are discrete time.
Yeah,
it's just the other 10% is annoying.
Exactly. So Dataflow programming, you are always assuming discrete time, and you're fine with that. That's a really interesting question, and it's not something that I would know how to do. So thank you.
I wish I could remember anything about what Matteo was doing, but he never. I don't remember whether he had a complete solution or not.
Okay. And perhaps something to ask. It would be interesting.
Any last questions before we end the live stream? Okay, let's thank Mario again.
Thank you.
Okay. We'll stop recording and stop the live stream. Toby, if you would. And maybe someone has more questions.